So where we left off last time, we were beginning to look at an example of numerical integration, and we were using the trapezoid method. So remember, we need to calculate the area of each of the trapezoids that we're going to create. And the equation for the area of a trapezoid is pretty easy. Just look at the average height, which would be 1/2 y1 plus y2, and multiply by the width of the base, which is just x2 minus x1. And so the example we're going to look at, we're integrating 3x squared minus 6x with respect to x from the limits x equals 0 to x equals 4. And we know that the exact answer is 16. So let's switch over to Excel and let's estimate that integral in Excel. So I'm going to create columns for x and y to start with. And we know x needs to go from 0 to 4, so there are 4 equal increments here. And in the y column, we put in our equation. It's equal to 3 times x squared minus 6 times x. And we'll copy that down. So there are our values of x and y. Now, of course, there are 5 points, but there's only 4 increments. So we start with finding the area. We'll start with the second row here. And so the equation for the area of a trapezoid is 1/2 times y2 plus y1, in other words, the average value of y, multiplied by the difference in the x values. And again, let me center that and copy that. And so those are the areas of our 4, in this case, trapezoids, and we'll sum those and see that our answer is 18, as we showed by hand. Now, if we wanted to get a little bit better estimate of that, I'm just going to copy these cells over here. And instead of every 1 unit, I'm going to go every 1/2. Down to a value of 4. So what that means, of course, is I'm going to be using 8 intervals instead of 4. And copy that. And I can actually copy the equation for the area. Copy that as well. And now sum that up. And now you can see, yeah, we get a lot closer to our exact value of 16. We have an answer of 16.5 right there. Okay, so here was our estimate with only 4 intervals used. And what you notice is we ended up with a value of 18 as opposed to the exact answer of 16. Because when we look at the positive areas, you'll see that our trapezoids are actually overestimating the actual area. And when we look at the negative areas, our trapezoids are underestimating. So those errors add up. Again, if we were to do more intervals, in this case 8, we get the sum of 16.5, which we showed in Excel as well. The only drawback on that is that you have to add more rows to the spreadsheet. So how do I know? If I didn't know that answer was 16, how would I know that I've used enough? And again, if you don't know the exact answer, that's probably why you're using a numerical solution. So what you look at, or when does it converge to a value? So you keep using more intervals. Now, of course, in Excel, again, you have to keep adding more rows. That makes MATLAB a good solution for doing these kind of problems as well. The advantage of MATLAB is I can change the number of intervals very easily and not have to copy and paste a lot of rows. So we're going to write a MATLAB script here, and it's going to call it Numerical Integration, NUMINT, as you can see. And it's going to integrate any function that, as long as I save that to a MATLAB function, I call function int, so FUNINT. Then the script will integrate that for whatever limits and whatever number of intervals that I want to use. So we'll prompt the user for the limits and for the number of intervals. And so going back to our example, remember we're going to do this same example. So we've written a function, again called funint. Output is y, input or argument is x, and so y is equal to 3x squared minus 6x. We've saved that function. Now, here's our MATLAB script here. So you can see up top here we're going to prompt the user to input the lower and upper limits as well as the number of intervals. We make the increment then the range upper minus lower divided by the number of intervals, and so we start out, the sum's going to be the integral, but we'll start that out with equal to 0, and we pick the first values that would correspond to the lower value. So remember, we don't have an increment until we get to the second value that we calculated. So our for loop starts at 2 and goes to intervals plus 1. So remember, if we have, like in that previous example, we had 4 intervals, but we actually had 5 points because we have the endpoints there. So as we go through, we're calculating our value of x. We calculate the value of y, which is based on the function that we've input. And here is our equation for the area of the trapezoid. We add that to the existing sum, keep doing that, and at the end we print to the screen the value of the sum, which is the integral. Alright, so let's switch over to MATLAB for a moment. And you can see here is the function, and here is that script that we looked at. And so I'm going to go ahead and run that. And we're going from 0 to 4, so lower limit 0, upper limit 4, and if I type in 4 as the number of intervals, then we match up that solution that we got with Excel, which is 18. Alright, let's run it again. Same limit, 0 to 4, but now let's put in 8 intervals. And again, we get that an answer that matches what we did with Excel. So again, the beauty of using MATLAB is that I don't have to rewrite things to use more intervals. In fact, let's go to 10,000 intervals, and you can see, at least to MATLAB's short format, I have arrived at the exact answer, again, out to 4 decimal places. So again, you can see we match up those answers, and as we increase the number of intervals, then that does converge to the exact solution of 16. So there are other methods besides the trapezoid method. If you use some higher order functions instead of just a straight line fit, then you only need to, you can use fewer intervals to come up with a higher accuracy. As an example of that, you might learn in your calculus class, Simpson's rule uses a second order polynomial. So instead of just having the 2 endpoints, you do it over 3 points and fit a second order polynomial to fit that. And you find it will come to an exact solution, or rather to a more accurate solution, a lot faster. But the way we have computers now, as you saw, I put in 10,000 trapezoids, and it took almost no time at all to do it. So usually don't find those higher order algorithms to be necessary here. Trapezoid method works just fine, and again, if you have even a slow computer these days, you can do many intervals and get a good solution with the trapezoid method.